Yeah.
Okay. Good day, everyone. Thank you very much for joining APRU SWM Virtual Winter School. So today our session will be on plastic and sustainability. And this session will be chaired by Professor Yong Sik Kok, who is the Director of APRU Sustainable Waste Management Program. So today we have three plenary speakers. First, Professor Cheng Gu from Nanjing University in China. And then we have Professor De Fu He from East China Normal University in China. And then we have Professor Sutta Kaudir from Chulalongkorn University in Thailand. And then we have three student presentations. First presentation from Yura Cho from Korea University. And then we have the presentation from Chao Wang from Nanjing University in China. And then we have the last presentation from Virin Kartitam Wong from Chualang University in Thailand. So now I would like to invite Professor Ok to take over this session. Thank you very much.
Yeah. So, hello everyone. Thank you very much for joining this second virtual winter school during your busy schedule. We successfully hosted the very first virtual winter school in last time that was led by Professor William Mitch at the Stanford University, who is a co-director of this APRU Sustainable Waste Management. Today also we got a full participant with 5 APRU Sustainable Waste Management Program leader, as well as program director, and main participant are the student from each group. So today, as just mentioned, we have total 3 plenary speaker. After that, we'll have extensive Q&A session. So I guess today we want to talk about the plastics and sustainability, particularly the weathering process of the plastic that will be read by Professor Cheng from Nanjing University. Myself and our APRU group student visited Nanjing University in 2 years back in a Christmas holiday season and had a very impactful discussion and got impressed by the advanced facility there. And our second plenary, Professor Dafu He is currently leading the microplastic monitoring, particularly in soils. As you, so just let me briefly explain. So as you may know, our current problems are complex. So notably, the climate change is not a single problem. So yeah, the COVID-19 pandemic has led to a surge in plastic waste, making the implementation of a sustainable management solution more urgent than ever. So as you know, in December last year, we hosted a very first Nature Forum on plastic and sustainability, the first of its kind to be held here, along with chief editor of Nature Nanotechnology and associate editor of Nature Review, Earth and Environment. We had over 1,000 international researchers participated and discussed the current challenges in plastic waste management, the impact of microplastics, and potential solutions that are aligned with the UN SDG. So the forum presented an opportunity to shine a light on neglected challenges, such as the accumulation of plastic waste in soil. So our second speaker today is invited plenary speaker. So he will address the issue. So as you know, the public is aware of the plastic pollution in the ocean, but plastic pollution in the soil is an ever greater concern as it affects food security and human health. So we need to change the paradigm through our APRU Sustainable Waste Management community. And in my personal viewpoint, like soil organic matter, plastic is basically carbon. So it's easy to collect plastic floating in the ocean. It's relatively easy, but plastic in soil is buried. So as a result, no one has looked at how to address this. If you remember our nature forum that was just held a month ago, as I mentioned, we got a more than 1,000 registration. And one of our speaker, Professor Matthias Lillig, talked about the importance of the carbon input, which comes from the plastics and global changes drivers. That was recently, plastic in soil is recently highlighted in Science and Nature. Even for the last week's Science has soil biodiversity paper have been published at the policy forum. So I just observed nowadays all the major journals in Nature Science and Cell publish articles on plastic in soil or plastic in the environment. So this topic getting more and more important. So I really hope we could have discussion, particularly among the students today. And we also have our program leader for today, Professor Chi Hwa Hwang from National University Singapore. And this April, Professor Chi Hwa Hwang, together with APRU, Sustainable Waste Management Program, Sustainable Waste Management Virtual Conference will be held and led by National University of Singapore, co-organized with our program. So I also hope all of you could join this important meeting organized by the APRU Sustainable Waste Management jointly together with American Institute for Chemical Engineers. Okay, so just let me turn it to Kumu so that she can continue for session this chair. Thank you.
Thank you very much, Professor. So let's start the first presentation, which is from Professor Cheng Gu. Professor Gu, could you kindly share your screen?
Hi, hello. Can you
Yes.
hear?
Yes,
Okay.
yes, we can.
So,
Okay, thank you.
so let us briefly introduce Professor Chang Gu at first. So Kumu, can you
Okay.
shortly introduce Professor Chang Gu?
Um, yes, Professor Cheng Gu is a professor in School of Environment, School of the Environment, Nanjing University, and Professor Gu obtained his PhD in environmental chemistry from University of Wisconsin, Madison in the USA, and he worked as a postdoctor in Michigan State University in the USA. And then he joined Nanjing University as a professor since 2011. And Professor Gu is currently the Changji School Distinguished Professor and the recipient of National Science Funds for Excellent Young Scholars. And he is the chief scientist for National Key Research and Development Plans. And Professor Gu's research focuses on the transformation of organic contaminants in natural environment, and he has published over 100 scientific papers on high impact factor journals, and was issued 8 national and international patents. And Professor Gu is the associated editor of Bulletin of Environmental Contaminants and Toxicology, and journal editor for environmental chemistry as well. So it's over to you, Professor Gu. Thank you very much.
So thank you, Kumu. Before we further proceed, just for student participant, Professor Chang Gu did his PhD at Wisconsin Madison. That's the headquarters of soil science in the world, especially in the US. So all the renowned soil scientists are actually there, and he did his postdoc at Michigan State University. That his supervisor was one of the most well-known scientists, particularly in the field of the organic clay. And Professor Gubin who continuously published a high quality paper, including ESNT that a few highlighted as the front cover or the back cover, that, as you know, in the field of environmental science, ESNT should be the most respected journal among the all journals in our discipline. Actually, in our discipline, we have more than 300. We have more than 250 SCI indexed journal in the field of environmental science. So please welcome for his presentation. Thank you very much.
Thank you. Thank you, Professor Oak, for your invitation. So today I just very briefly talk about some of recent studies on microplastic. So my topic is photoaging of microplastics and the effects on the environmental behaviors of some antibiotics in aquatic environment. So just first of all, I gave some very basic information about this, some background information about the microplastic. So with a vast production of plastics, so now you can find plastic everywhere, from polar regions to the equators, and also from the seabed to the mountain top. So with the microplastic is plastic with a smaller particle size. Usually we think like if the plastic size is smaller than 5 millimeter, so they are called a microplastic. The source of this microplastic is from two sides. One is they probably be produced from some primary sources. So through some for example, the face cleaners. So there are some scrubbers, the plastic as a scrubbers inside the, these things. So this intentionally produced. Another source for the microplastic is that they from the decomposition of the plastic product. So after several days or several years, the plastic is becoming very brittle. So it's easy to be decomposed into smaller size. So due to the small particle size of these microplastics, so they can have pose the potential risk for organisms. So one of the risks is that organic contaminants or some heavy metals can absorb onto the microplastic surface. Transportation for these plastics in the environment. So this contaminants can be very toxic for the aquatic organisms, or some also in the in the ocean too. So in my research, so we mainly focus on the PVC microplastic. The PVC microplastic, this plastic are widely produced in China. So China is #1 producer of PVC now in the world. According to recent studies, so some Chinese science researchers, they studied the PVC particles in the Pearl River. So the concentration of this PVC microplastic be as high as 400 pellets per cubic meter. So the concentration is very, very high. So after PVC, these microplastics are released into the aquatic environment. So the natural photoaging of microplastics are generally considered as a very slow process. However, some studies, including our recent papers published in ESNT in 2019, we found that under environmental conditions can be accelerated. The degradation of this or the decomposition of these microplastics can be accelerated, especially under some radical attack. So these radicals mainly for the reactive oxygen species. You probably already know that that's including the hydroxy radicals, This also, and something like the carbon anion, oxygen anions too. So this ROS or reactive oxygen species can accelerate the aging process of microplastic in aquatic system. So it's necessary to investigate the phototransformation of this PVC microplastic in the presence of reactive substance that are able to generate this ROS under natural conditions. So then we think about the low molecular weight organic acid, for example, the oxalate or citrate, because this low molecular weight organic acid are commonly distributed in the environment. They can be excreted by the bacteria and or some microorganisms. And the studies also show that, so this like oxalate or citrate, and their ferric complex can produce reactive oxygen dioxide radical anion upon the photoirradiation. Subsequently, the carbon dioxide radical anion can transform into this reactive oxygen species by interact with oxygen molecule. So we can expect that the presence of this natural organic acid could promote the aging process of this PVC microplastic. So we did some experiment with like the PVC, and also with the PVC in the presence of some low molecular weight, like in this case is oxalate, and oxalate with iron 3 complex. We also found that even the PVC can underwent direct photolysis. However, when the process, when the system, when add the like the smaller molecule organic acid, so the aging process can be obviously accelerated. So this is also with different size of this the microplastics. So with smaller size, the aging process is more obvious. It's an acceleration process by this oxalate. So oxalate with iron 3 complex, the aging process will be accelerated with smaller size. Even we use 10 micrometer. So the increase for this degree for this agent is continue to increase. So we use 2 micrometer. So it indicates that, it clearly indicates that the presence of this oxalate and oxalate iron 3 complex could promote this aging process, because for the PVC microplastic, it has chlorine inside. So we do see the chlorine dechlorination for this microplastic. This as an indication for the aging process. So then we use some like the EPR. EPR is a technique to detect the radicals, in the system. So we use the EPR, and also we use the nitro blue tetrazolene chloride. This also tests, like the radical formation. This is kind of the pro molecule. So we found that the production of this carbon dioxide radical, and also we found the hydroxy radicals when this oxalate and oxalate iron 3 the presence in the system under the photodegradation, simulated sunlight irradiation. Then in our system, we monitor the surface change on the PVC microplastic during the photolysis. We use something called the in situ micro ATR, FTIR spectroscopic device. Then I give you several slides to introduce, how this technique work and how to prepare a sample. So the PVC sample was put in a sample holder here. and the IR spectra were collected in situ collected. So this slide shows that. So is how we prepare the sample. So this is a reaction cell. The left side. This the photo shows that the reaction cell. This custom made stainless steel the cell. This reaction is inside this the cell. So we can immobilize this the PVC microplastic into this cell and fix onto the special place. So this indicates that the single particle are fixed there. So then we do the irradiation photo irradiation exposure, by the specific particles. So after irradiation for specific time, some period, we take sample to analyze the sample after the photo irradiation. So it means that so in the last this photo, the right bottom photo is how we do the data collection. So the sample is in one of the grid. So this is the interface of this microplastic ATR FTIR system. So operations interface. This including the green circles showing that the scanning areas, and also we get the bottom spectra is FTIR spectra, and this red and like pink color. This is a two-dimensional image. So the analyzed surface is 100 micrometer, 100 micrometer times 100 micrometer for a square. So for the the sample corresponding to a grid of 10 points in both x-axis and y-axis. So we totally have like 100 points, on the surface to using this micro ATR FTI to scan the surface. We can get the like the two-dimensional IR spectra. The color shows that here, shows that the difference for the different functional groups. The darker color or is a different color means that there's a different concentrations for this for these different functional groups. So this is how the instruments work. Then we look at the IR spectra that after aging, we do find some new absorption bond corresponding to the carbon-carbon bond, and this the carbonyl bond, and also this hydroxyl stretching vibrations. This new peaks appears, indicating this in the system. We found some dehydrochlorination reactions and also some oxygen reactions occurred during this photoirradiation process. Furthermore, if we compare the IR spectra of this PVC and also with PVC with iron 3, it's no oxalate in the system. So we can conclude that the presence of oxalate and oxalate iron 3 can significantly accelerate the generation of this double carbon bond and also this carbonyl groups, and also including the hydroxyl groups. So it means that it also support our experimental result that so the presence of this low molecular weight organic acid can accelerate the aging process, also produce some like the functional groups on the surface. Then we gave a pathway. So there are 3 pathways. One is direct light irradiation dechlorination. So on the surface of this, on the surface changes of this PVC microplastic are proposed according to our spectroscopic results. So when exposed to the solar irradiation, dehydrochlorination reactions undergoes with the production of carbon cations. then they can further transform into the alkene and polyene structures. That's product 2 on the aged PVC polymers. So as shown in the route 1. In addition, oxygen molecules can also involve in the dehydrochlorination process. That is route 2. The product 2 is a conjugated carbon-carbon double bond, and product 3 with unsaturated ketone and alcohols are produced. As this is route 2. Furthermore, since hydroxy radicals are produced from the oxalate and oxalate iron 3 complex and simulated sunlight conditions, the alkyl group on the product 3 can be attacked by these hydroxy radicals and transform into the carbonyl groups to form product 4. That is in route 3. Subsequently, the product 4 can be further dechlorinated upon the photoirradiation or the hydroxy radical attack to form product 5 and 6, respectively. In addition, product 6 can be further oxidized by the hydroxy radical to form a polyketone product as a product 7. So this is already published in water research is in this year. So if you are interested, you can find this paper. So after the aging process, we do found some, oxygen-containing functional groups are produced on this PVC microplastic surface. So we do test, the absorption of this ciprofloxacin antibiotics, which is also a common antibiotics used, for human and also for animals. So this antibiotics absorption, on this PVC microplastic surface is also significantly enhanced. So that's because that this ciprofloxacin antibiotics are a polar compound. After the organic, after the PVC microplastic are aged, we also add some hydrophilic groups, so they may increase interaction between this, the more hydrophilic aged microplastic and this polar antibiotics. So they increase absorption of this common antibiotics. So after we did the absorption process, we found that after aging process, so this aged microplastic can increase absorption for antibiotics. Then our next question is that whether we can see some surface catalyzed reactions after the microplastic are aged. So this is our hypothesis. So then we use cefazolin antibiotic as an example. So as a model compound to study the interaction between this antibiotics and PVC microplastic. We use pristine PVC microplastic and also with aged microplastics. So the PVC for this studies, the PVC microplastics are initially aged by UV radiation. So as shown in the figure that the photo-aged PVC microplastic appeared harsh and uneven compared to the original one. And also a significant decrease in contact angle was obtained. So indicating that, so after aging, this microplastic has higher water affinities. So at the same time, the content of its oxygen also in this aged microplastics also significantly increased. It's analyzed by the XPS analysis. So then we did some experiment using the cefazolin. This is also common antibiotics. We did an experiment at pH 7. So we do see that after, if it's only therefore zoline, it can degrade about less than 20% after 7 days reaction. However, in the presence of pristine PVC, the degradation rate after 7 days only 16%. But with aged, aged PVC microplastic, the degradation rate or the removal rate, we found that it's almost 45%. So it means that a significant increase for the degradation was observed on the surface of aged PVC. So under environmental relevant conditions. So then we analyzed the degradation product. We found that a hydrolytic degradation pathway was proposed. So by opening the beta-lactam ring, so we also test the mass balance, that the mass balance can reach over 95%. So it indicates that the reaction surface of this aged microplastic can catalyze the hydrolysis reactions of this, the daffodilin antibiotics on the surface. So it's a very interesting result. So then we did some experiments with FTIR spectra. So compared to the pristine PVC microplastic, we do see the significant enhancement for the intensities of this daffodilin antibiotic characteristic peaks were observed on the surface of aged PVC microplastics, especially for the the carboxylic group and also the carbonyl groups. So which can ascribe to the great absorption of this beta-lactam on the aged PVC microplastics. And then if you compare with the original PVC microplastic. So we also, more importantly, we do find the red shift on the carbonyl peaks of the sulfazolin on the sulfazolins with this aged PVC particle. The peaks of this carboxylic group, the asymmetric vibration of this carboxylic group, and the carbonyl group of these antibiotics are getting wider and red shifted upon this the daffodilin absorption, indicating the involvement of this hydrogen bonding of this ketone in the beta-lactam ring, and also the carboxylic groups to the surface hydroxyl and the carbonyl group on the surface of this aged PVC microplastic. So we do see the interactions between this aged microplastic and this antibiotics. Right? Sorry. So then we did some theoretic calculation. Based on the the calculation, we simulate the intermolecular interactions and also the geometrical structures between this daffodilin and PVC. Interesting, the positive Mulligan charge of this carbon atom in the beta lactam ring increase from like 0.563 to 0.579 for the daffodilin on the edge of PVC compared to the original PVC. It's supporting that. So the hydrogen bonding forces between daffodilin and also the PVC could facilitate the water-induced nucleophilic attack and the subsequent hydrolysis reaction. Then we get a quick summary for this research. So the photoaging of PVC microplastic can be enhanced by the hydroxy radicals derived from natural organic acid. The photoaging PVC microplastic exhibits stronger absorption capacity for polar antibiotics than their original powders. The last one is photoaged PVC microplastic could accelerate the hydrolysis of antibiotics by forming intermolecular hydrogen bondings. So last, thank you very much for your attention. Thank you.
Thank you very much, Professor.
Mm-hmm.
Are there any questions from the audience?
Yes, I have a question.
Mhm.
Thank you very much, Professor, for the presentation. I am Christopher Nzediegu. I am calling in from Canada. I work with Professor Scott Chang. So my question is, there was a slide that you showed us the different transformation products of PVC. So I was wondering if you are interested, if you're going to be interested in understanding the toxicity of the different transformation products of the PVC. How toxic are they? Are they going to be less toxic than the PVC or more toxic than the PVC itself? And I was also wondering if you are able to identify what those transformation products are, like their names. What are their names? Because I just saw you put them as P1, P2. Do we know their names? Thank you.
Okay, thank you. All right. So, well, so thank you for the question. So, I mean, like, because let me see the product. So this is just some pathways. So this formation, the product of this photo irradiation is that, so this on the surface is not really released to the solution. So as I expect, after we didn't do any toxic test, sorry, but as I expect that because after the photoaging process, so the system is the surface of this PVC microplastic is becoming more hydrophilic. So it means that some like hydrophobic contaminants, for example, the pH. So the associated with pH may be decreased. So that is so if this is the case, so like the toxicity of this microplastic may becoming less toxic for the organisms. But because they can absorb more the hydrophilic compound, for example, the antibiotics, they may increase the toxicity. So this different for different compound for different contaminants. So it's not difficult to say. But for us, we didn't do any toxicity test. And
okay.
the product we can we can identify some of them. Yeah.
Then I was also wondering, was it only contact angle method that was used to assess the hydrophobicity or the hydrophilicity? Was it only contact angle method?
Yeah, we did the contact angle test. We only did the contact angle test, to confirm like the surface is becoming more hydrophilic. So this is the only test we did. Yeah.
Okay, thank you.
Sure, thank you.
I have a question.
Yeah.
Yes. Hello, my name is Sehan from Korea University. I have one question. I'm planning for experiments for put PVC in soils and see the effect. And I want to ask you what kind of PVC is the best for that? For see its effect on soil.
So you mean like the PVC product will affect the soil, right?
Yeah. Yes.
So after aging, right?
Yeah.
So yeah, it's also same thing like because we didn't do any toxicity test. So I mean, for the for the soil, I think that's also soil also have like a similar aging process, especially on the surface of the soil because they also have sunlight. And our research started, as it's not published yet. So we found that, and we control the humidity of the system. For example, like we use very extremely dry conditions, and also add some like humidity in the system to simulate, like the soil. So on the surface of soil, the aging process. We do find that under some with some water content, it can accelerate, also can accelerate the aging process compared to the extremely dry conditions. So so the reactions I just I present here, I think also can occur in the like in the soil environment too. But you know, like after aging, the same thing is like it's more becoming more hydrophilic, so they can, you know, some organic, some polar organic compound can be associated with, you know, like with this microplastic, PVC microplastics. Yeah, I didn't mention that our second part for the, you know, like the catalysis of this the hydrolysis reactions. This we haven't published yet. We're almost ready to submit. We will submit to ESNT. But the first one we already published in Water Research last year. Yeah, you can if you are interested. Thank you.
Thank you very much.
Mm-hmm.
Thank you, Professor.
Oh, can I ask one more question?
Yeah, we can get one more question, and at the end we have like Q&A and panel discussion, and there we can take more question. Yes, Seung, you can ask your question.
Okay, thank you. Thank you for presentation. And I'm Seung Kim from Korea University. And you said, as you say in the presentation, you told that there's a dechlorination by the UV, and that is make the PVC more easy to decomposition. And do you expect that the same reaction will be happen that other plastic that has chlorine due to the UV?
Yeah, I think so. I think this reactions probably is common for the for other plastics, even without, you know, like the chloride. They can also do the they can follow the, you know, they can form the carbon-carbon bond or the carbonyl groups, add some oxygen into the, you know, the surface of this plastics. They can happen. Yeah, I think so. I actually we did something with the polyarene. Yeah, it's other plastic. We can find similar results. But the reason why I use the PVC, because in the PVC we can monitor the chloride concentration. It's an indication for the dechlorination. But other plastic can also do. Yeah, you also can undergo this aging process, you know, to add some functional groups on the surface.
Okay, thank you for answer.
Sure.
Thank you, and thank you very much, Professor Gu, for your comprehensive presentation and for the fruitful discussion. So now we can move to the next presenter, the next plenary speaker. Our next plenary speaker is Professor De-Fu He. He's an associate professor and also a research director at School of Ecological and Environmental Sciences at East China Normal University in China. And he finished his undergraduate study in Hunan Normal University, and then he worked in Hanwha University as a teacher until 1998, and then he obtained his PhD and became a faculty member at East China Normal University in 2003. From 2006 to 2007, he worked as a postdoctoral fellowship at National Neuroscience Institute of Singapore, and then he joined East China Normal University and working as an associate professor as well as a research director. And Dr. He has published over 60 scientific papers, and currently he his work mostly focuses on microplastic in terrestrial ecosystems. So I would like to invite Professor De-Fu, and it's over to you, Professor De-Fu.
Hello, everyone. Thank you very much for the introduction of myself. I'm De-Fu He from East China Normal University. Thank you, Professor Ok's invitation, and have opportunity to this meeting and see all of you. Professor Gu have just had a wonderful speak about the microplastic aging, mostly in the aquatic environment. And my speaking title is Effects of Microplastic on Soils, Nematode, and Sea Lichens and Snail physical. So the key background of the, can you see all of you? Yes?
Yes.
Can you hear clear?
Yes.
Oh, okay. The key background of the current microplastic issue is global plastic production have continued and fast increasing during the recent decades. But small part, about 7% of the plastic product are recycled, and the major most are released into the environment. So, in the fact, the majority of the plastic rubbish in the ocean come from the terrestrial environment and closely related to the human's activity. The left picture shows the overview of the transferring of the microplastic among different environments, such from the land to the ocean, from the land and air to the water environment. And the right picture shows the detailed source and effect of the microplastic in the soil, including the air positions, residue, sludge, overland, runoff, and the microplastic can be uptaken by the global plant and soil animals, and even transferring to the food chains of the human being. So this slide shows our result of the microplastic in the soils around the city of Shanghai, the university here, and the main source are the mature residues and the discard particle. This shows the evidence and the picture of the microplastic. And this shows a recent work about microplastic in the agricultural soil in the, at a larger scale across the mainland of China, and show the distribution of among different regions and different soil layers. For example, the North and the West North provinces have highest evidence of the microplastic, but the South and the West South show related low evidence, and with decreasing evidence from the surface to the deep soil layers. This is unpublished data. About the detailed analytical method, this shows the overview of the procedure for assess microplastic, including the sampling, pre-treatment, separation, and qualification. So different the sample con different the procedures. In our about the soil samples, including the several, the proliferation, and the filtration. We use the sodium bromide. We also use the cycle extraction approach like this picture. So including a cycle system and the solution, the solution can reside and reuse and to reduce the of the experiments. So in another study, we also found microparticles was contained with the body of the land-dwelling animals, usually as traditional medicinal materials, especially in China. So including the direct file, the sludge, critical and small soil animals, other soil animals. So this shows the deterred microplastics such as PET fiber, royal PE, nylon, PP, and PVC. So both the flesh of the animals or dry medicinal metals can be detected out microplastic containing in the body of the animals. So this shows a positive relationship between the flesh animals and the medicinal metal. So we then think whether the microplastics can affect the physiology of the soil animals. So we use two types of the soil animals. The first one is soil nematodes, and the other is land snail. The two type animals have the wide distribution in the soils all over the world. So first, we can see the result in the worms. This slide shows the impact of the microplastic on the survival rate. So we use the pure microplastic in different polymers type of the microplastic with similar size, but slight difference in packages in A. But use different size of the same type of PS, we found the different effectors. So in B. So we also found the influence, the microplastic influence the body's length, the egg numbers, and the blood size. So with different, most inhibitions with different percentage. So we most focus on the size-dependent effector. So we use the different size of the microplastic from small to the 5 micrometers, and we can show we can find that the content in the body of the animals, the lead microplastic. So the 1-pointed micrometers have the biggest distribution in the body. This shows the detail of distribution of the microplastic contained in the body, most in the digestive tracts. So this is red. So microplastic can result in the reduce of the lifespan. Also, the 1-point micrometer size show strongest effect here. Use the transgenic animals, we can find the significant increase of the expression of the GST4, which indicates the oxidative stress response in the animals after exposure. Also, strongest effect in the 1 micrometer size group here. So we can see that in tensile damage in the animals, this control the worm, this get in the intestine, and this is a exposure group. So you can see the abnormal intestinal willing, like here. So we continue to use the continuous animals. To show the decrease of the calcium indicator potent expression after exposure, which reflected the potential one of the mechanism of the intestine damage. We also found some abnormal expression of the function protein in the intestine, such as VHA6OP2 and NHX2. The first two is the protein of the calcium receptor protein, and this is the sodium ion and heavy ion exchanger related protein. So this indicates that the protein of the key protein in the intestine change expression show some mechanism. So we summarize the work started on the C ligands, including the number one, the size-dependent toxicity of the microparticle part on the growth and development of the nematode. And the intestinal tract gut is one of the main target organs of the induced the damage or by the microparticles. So the physical action are also pathological damage, including the damage. So oxidative strange and calcium-related protein are involved with the mechanism of the toxic effect of the microparticle. So in the land Snail experiment, we first used the PET microfiber. As you know, the fiber are major shapes type found in the soil or water environment. After food feed, 5 hours, and microparticle fiber can be uptaken by the snails and then distributed in the digestive organs, including global stomach and anatonic and postonic intestine. So here. And also microfiber discharged within 48 hours indicates that the microfiber denoters accumulate in the body of snail. So after digestion of the snail, can act on the microparticle, cause damage on the surface of the microfiber. You can see a lot of collect and the damage on the surface. And we also found a reduce of the diameter of the fiber. Use same treatment on the original fiber or the microfiber in the feces. So if you use a source microfiber exposure for 4 weeks, we can find the food intake and excretions later. Also, the shear diameter and shear length and no change, but this one change in the middle or high concentration groups. But in his pathology picture of the stomach, intestinal, liver, and the kidney, we found a slight or no obvious change. But some protein of the GPase, TAOC, and the MDA, the oxidative stress reactor protein, some change mostly in the high concentration groups. So the next, how about the response of the land snail on big plastic? We then use a common plastic expanded PS form, is EPS. So he showed the snail and the EPS and some vegetables induce the eat by the animals. This shows a video of eating the EPS you can see. So the animals move slowly and slowly, but can touch and eat the EPS. And then the development and the mass and substrate no change. But we've analyzed the microplastic residues in the feces. We can find a lot of microplastic residue in the feces and side distribution. So we can see the noise mark in the EPS, but we found analysis the mass balance. We found a significant mass loss, about 30% loss, comparison between the total PS consumption and the microplastic received in the feces. So by GPC analysis, we found a significant increase in the MN and MW, and the molecular weight distribution cover moved to the high directions. So it indicates a limited degradation and possibly degrade on the low molecular weight PS polymer. And FTR and HNMR also show that the formation of the functional groups to change the detail. So we also found a significant shift in the gut's microenvironment after the ingestion of the PS, some with an increase of the bacterial family like the Nato and the blue, but some reduce like the yellow. So at gene levels, the gut bacteria community also shows similar change. B. Moreover, we use the antibiotic suppression. I use OT. So 5 days feed the OT, the total the bacterial the community reduce. And in this situation, we simply let the snail to feed with the EPS. We also found that the MN and MWs increase, which is similar to that without the antibiotic inhibition. So it indicates that the finite decomposition of the PS in the snail is independent of the activity of the intestinal microorganism reduced inhibited by the OT. So we summarize the study on the soil snail. So number one, so in interaction between the microparticle and the land snails. Number two, so at one hand that the microparticle can be ingested by the snail without long-term accumulation in the body, but induce a slight and some physiological response, some gene expression and protein change, mostly in the intestine. And snail can eat and ingest the EPS discharge microparticle in the feces and partially biodegrade the PS. So say some conclusion about our work on the soil, the microplastic in soil and the soil animals. We can find the microplastic pollution is widespread and calm world and wide influence the source by physical environment and especially on the topsoil of the landers. So microplastics have marked impacts on soil elements, and the soil elements can sometimes adapt towards the microplastic pollution of the soils. The last is the soil elements can influence the fate of the microplastic or plastic. So by the digestion, fragmentation, and biodegradation, the partially biodegradation by the Snail in our study. So this is the conclusion. So this shows our publication, especially on the microplastic out, mostly about focus on the soils, the ecotoxicology, and the environmental behavior in the soil. In this sense, we also have published a book, special in the microplastic in the Thailand environment. So this just have been published in the end of the last year. This is as one of the handbook of the environment chemistry. So it's very popular in the internet and have highest of the download and this is free download. You can download on net. So thank you very much. This shows our university, the two campus, East China Normal University, and this some members of this work in our level. So thanks. That's all. Thanks.
Thank you very much, Professor He. So due to the time limitation, we can take 1 to 2 questions. So are there any?
I have one question. Yes. Thank you for your presentation, Professor He. And I might give just brief 2 questions from your presentation. One is that about the method. I wonder how could you separate the plastic particles with the size? As you've shown, it was 0.1 micrometer and 1 micrometer. So was it separated from the beginning, or you could have some treatment or method to separate the plastic particles with the different size? And the second question is for the microfiber application. When you apply the microfiber for the experiment, how could you homogenize that fiber if you cannot, or you can measure the size of that fiber or to make an average of this size? How can you homogenize this microfiber before the experiment? Yeah, I just want to know that method you have done.
Yes, thank you. Very good. The first one, you say the 1 micrometer size it have a strong effector on our study. Use the choice nemos and totals. Yes, we think this most use the highest distribution of the 1 micrometer is related to the size of the mouth of the animals. You know, the worms in the soils are, but the nematode is a very small animals, about the legs about 1 mm. So the mouth is very small, but if too big microplastic, he cannot uptake by the animals, but very small. So maybe he can pass through the digestive tract and discharge in the feces. So if a medium size just can stay in the tract, so a long time to enter with the wall cell of the intact. Do you understand it? So this makes one reason, is a major reason. This also adapt to other animals. The second question, you say that microfiber, or I'm sorry, you can how to make and how to the effector. You say
how to homogenize the size of microfiber, because it could be in different lengths before we apply. So how could you make an average of length, or yeah, how did you treat before used it?
So this by manuals to first found that the raw fibers by other chemicals we buy from the chemical, and then by made by students and cut, and also use a slice, cut, and same size, and then stem, and after stem, after stem, and then feed by the animals. So we can easily can easily find it in the tract, the digestive tract. So this is no problem. Thanks.
Thank you.
Are there any questions from the audience? If there is no question, we can move to the next speaker. So our next plenary speaker is Professor Sutta Kaudiar. He's an associate professor at Department of Environmental Engineering, as well as director of Center of Excellence of Hazardous Substance Management at Chulalongkorn University in Thailand. And Professor Sutta received his BSc Engineering from Environmental Engineering at Oriang Chulalongkorn University, and then he obtained his MSc and PhD from Environmental Engineering at Oriang State University. And Professor Sutta also serve as environmental National Environmental Board, and also serve as head of Department of Environmental Engineering. Also, he served as a director of the International Postgraduate Program in Environmental Management at Chulalongkorn University. So today he will give his presentation on material flow analysis to promote circular economy development, case study on post-industrial plastic waste in Thailand. So I would like to invite Professor Sutta for giving your presentation. Thank you very much.
Thank you. Can you see my slide? Not yet?
Not yet.
Okay, let me try again. Okay, good afternoon, everyone. Today, I'd like to talk about one of my work related to plastic waste management. So from the first to professor, my talk would be a little broader, okay, in terms of the boundary of the work. This is the material flow analysis. So still, we are using basic engineering tools on material balance and try to see where is the plastic waste come from and where it's go. And one of the problems is Thailand is one of the country. I think we are in the top 10 that people are saying that we are one of the top 10 countries that produce marine microplastic in the world. So being said, the government is trying to see where this plastic come from, and we try to account for the number of the plastic that we are using in the country and try to see whether it's end up in the marine. Okay, so this work, I'm working with two of my colleagues, Dr. Ampira and Dr. Manit. Okay. Plastic waste in general, I have some of the picture. These are the real waste management site in Thailand. Okay, many of the plastic is not easy to collect, and once it's been used, sometimes it's not easy to separate at source. It contains a mixed waste. It can be mixed with other plastic and also mixed with the product that they're using for. In Thailand, we use a lot of plastic for food. So sometimes and many times it contains a lot of food residue with the plastic. Okay, and the improper waste management left the plastic waste and it's entered the environment. Plastic waste, once it's entered the environment, it's not easy to biodegrade and it's persistent in landfill. And it's of course one of the source of the microplastic that the two previous speakers that mentioned about. Okay, this is the general number. We can see that by business as usual, the consumption rate in the next 30 years, probably we will generate 4 times more plastic waste than we have today. And this is the number that we are very concerned. Okay. In Thailand, there are many measures that we try to reduce the plastic waste, limited the plastic waste, especially the single use. We try to ban many types of plastic. So that's starting from 2-3 years back and starting ineffective from now. And hopefully we see some of the results in the near future. Okay. These are some of the plastic products that I use in the study that we choose to looking at in the study. So we give you the number of HDPE consumption in Thailand, say in 2018. We can see that most of the HDPE we are using for bag and bottles. So that that contribute to more than half. So we use HDPE for bag and bottles. And for PP, it's basically it's about the same. So we use it for bottle, for bag, and film, and other things. We come back to that later, but I want to introduce that film is one of the problems that we have in Thailand. How do we know this is the problems? If you're looking at what we are trying to do, normally plastic in Thailand, more than 50% has been collected and resale or recycle. So we are doing very good with that number. But once you look at the final disposal place like the landfill, you see a pattern. There's only few type of plastic that entering disposal site, which is mean, go back to what I said earlier. These are the plastic that is not easy to separate. It's normally mixed with other waste. And many times the cost benefit is not that great. So in order to try to separate, reuse, resell, or recycle, people tend to ignore and dispose it. So it ends up in the landfill. And that's mainly film plastic. Film plastic is something that you use for closure, and it's normally light, and when we resell plastic in Thailand, normally we go it by kilo. It is very difficult to collect a kilogram of film waste plastic. So that's why one of the reasons that normally people doesn't care that much about plastic film. Okay, so like I mentioned, so we go looking at the landfill and we try to figure, so if we want to go to zero waste or reduce the waste to landfill, increase the portion of plastic going to recycle, I think this is a very good place to start. And we found that in landfill, it's about 30% organics and about 50% other waste, and 20% of the waste stream entering landfill in Thailand is plastic. And through those 20%, it's mainly bag, okay, and bottles, bag and bottles. So I have a picture on the right of the screen showing both sides, the right and the left, showing the kind of plastic that we normally find in the landfill. So what should we do about this? Okay, so we try to go back and tracing the plastic from the production to the end use. And in Thailand, the system of industry is quite easy to follow and as a starting point, because the industry required to register how much waste they produce. So I think that's the good starting point. And so we divided into 3 or 4 groups that we want to go and find out the number and what kind of plastic that they use, what kind of waste plastic that they produce. The first of all is the plastic fabrication production and plastic packaging production. Okay, and then we're looking at the industrial consumer, which is other industry that using plastic. Okay, the main user of plastic in the industry are food industry, electronic equipment industry, and consumer product industry. Okay, so in general, like I mentioned, so we want to try to stop the plastic going into place that we don't need, for example, into the sea. So we want to do the material balance and try to get all the plastic coming back within the loop. So we need information, we need to design something that more environmental friendly, and we need to set up criteria and new waste management scheme. Okay, this is a very good picture of how we set up the study. Okay, we try to do the material balance on plastic in terms of country level. Okay, we do it in terms of country level. In Thailand, how many plastic that we are produce, how many plastic that we are using, how many of them going to waste, how many of them going out of this loop and end up somewhere else that we don't need. Okay, and we think that sustainable resource and use of circular economy can use the concept of material flow analysis in order to see what happened. Okay, so we know how much has been used and we know how much can be recycled and how much is missing. So by doing so, hopefully we reduce the leakage of plastic into the natural environment and also reduce the plastic that made from fossil feedstock. Okay, so the specific project that I'm using as the example today is the post-industrial and post-consumer industrial plastic film waste survey in Bangkok and nearby province. I already mentioned the importance of film waste because film is very thin and very light. The value is not a lot and people try to avoid recycle it. So it ends up mostly in the landfill. Okay. So the study, we do the plastic waste flow of film waste in the industrial sector. Okay, and then try to identify the target factory as the example of the producer. Okay, see the generation and flow of their waste management and try to make it in terms of a bigger picture. Okay, this is the Thailand in 2015, the plastic that we are using in each sector of the industry. Okay, we see that I already mentioned that packaging and electrical appliance are the main user in the term of plastic. Okay, and we use about 5,000 kiloton in 2015, and mostly packaging. Okay. Okay, and so the study started out with the survey, and we already have some data from the government office. So we select 5 post-industrial scrap industry, try to see how they produce plastic. And then we select other 15 industry for the one that use in the plastic as the post-industrial consumer. And then we do the 10 site for commercial consumer, including exhibition center, home mart, distribution center, airport, and hotel. The number in the parentheses is the industry code. So in Thailand, we have 108 industrial type. So the code indicate that this kind of industry using plastic in the process. So there are 16 types that identify that using plastic and producing plastic waste in the process. So we want to know how much they use, okay, what type of plastic that they use, what type of plastic waste that they produce. We also have a waste code for every industrial waste, and plastic waste code consists of some number, so we can easily track that back into the database of the government, okay? So we want to know how many plastic waste that they dispose in a year, okay, how much in weight and volume. Sometimes we cannot relate it that by a questionnaire. We have to go into the site and measuring and try to get some representative of the waste and convert that back to weight and volume, okay? Okay, and then the frequency of the time that they discard their waste, and then we try to do the material balance and then come up with the amount of waste disposal per year, okay? This is the overall material flow analysis. Basically, this is the product that we are looking for. And the process of doing this take quite some time. And we have to do it. This material flow is just for a certain period, specific time. For example, this is for the year of 2018. So by the time it's 2019, we can come back and recheck the number, and hopefully we get more details, more data. But in general, this is what we got at 2018. On the left side is the film production part. So we go to 5 industries and try to see what type of plastic that they produce and how they manage their waste. Okay, and plastic waste from the industry at kind consists of packaging waste, production waste, and other waste. Production waste come from the leftover, the trimming, the shaving of plastic. So normally this can be recycled easily. Okay, and in the middle we have industrial consumer and commercial consumer. Okay, industrial consumer, so we use that in many industry, including food, beverage, electrical appliance, consumer product, chemicals, and automotive. If you're looking at that, okay, there are 3 options of waste management. Okay, first of all is sellable. So anything that can be sold. Okay, this includes PE clear films, PE mixed color film, and other films. And then there's non-sellable. Okay, and then there's some industry that they don't even care to separate their waste. So if the thing that going out from the system, they go to the far right. So there are options of waste management, including recycle, fuel blending, incineration, and sanitary landfill, and then energy recovery and resale again. On the bottom, you can see the commercial use. Again, we separate the plastic waste into sellable, non-sellable, and no separation. Okay, and then most of the municipal waste go to incineration and then landfill. So by putting the number into this diagram, okay, you can see how much it go where, okay, and what are the problems, what might be the problems, okay. This is just to show you that plastic films, okay, I mentioned many times, if you separate plastic into film and rigid, the rigid part is something that is more valuable and it can be resale. And we can see that even though film, you see that it's about 20 to 30% of the plastic that generate plastic waste, still these are the waste that cannot be recycled effectively. Okay, these are some of the products that we are considered a plastic film. You can see that it's light, and normally this is what we find in the landfill. Okay, so these are the details of the plastic waste generated in Thailand. And when we put in the number, we can see that for plastic film, even though it's not a lot, still that a lot of consider it still can cause a lot of problem in terms of plastic bag, film, scrap parts. These are the ones that we have problem with at the moment. Okay, these are the type of film by factory. Okay, the factory code indicated what kind of factory in Thailand. I mentioned it's 108 type of factory. So the factory that normally use plastic and produce plastic waste are meat product, food from milk, beverage, plastic products, for example, electric equipments and printing production. These are the type of plastic that they generate and amount of plastic waste that they generate in ton per year. Okay, and again, okay, this is to emphasize how important that even though film is not 50 or 60% of waste plastic, still these are the portion that end up unmanaged, end up in the landfill and cause the problems to the environment. Okay. This is the management option. This is management option. We can see that if we're looking at the recycle rate and resale rate, we are doing not too bad. We're doing very good. It's more than 60% is recycle. Okay, and besides recycle, we do have coal incineration with the cement production. We use it as fuel blending. So a lot of them going to some kind of use after that. Okay, but only a few that go to landfill, but still 15%, and that's the one that causing the problems. Okay, by saying going to landfill doesn't mean that it's always going to landfill. It's something that missing from the management scheme. Okay, and we are trying to do the social part as well. We try to ask them why they not separate their waste. Okay, so it's end up that there's no place and there's no benefit of doing it, all the way to it's not interest. So these are something that we like to see, and we like to promote in the future how to change their mind. Sometimes they just use the subcontractor to manage their waste. So by doing that, the company itself doesn't need to separate their waste at the beginning. Okay. So in conclusion, okay, come back to the first point that I mentioned. We are using material flow to identify the source and the flow of plastic waste in Thailand. So, and the film is about 30% of the waste plastic that generate. Okay, it is including bags, film, wrap, bubble sheets, snack bag, label, and tapes. Okay, and the top 5 contributors are plastic converter, consumer product, food, and electronic. Okay, and we do a very good job, like I mentioned, about 60% has been sought and resale. Okay, and the reason that there's still no separation maybe is the time consuming, the cost, and the lack of area of storage. Okay, so this work is the work from my center, working together with the Petrochemical College, Chulalongkorn University, and the Suez Service, which is the company in Thailand working on waste management. So thank you very much for listening. We're glad to answer the question. Thank you.
Thank you very much, Professor Kaudir, for your informative presentation. So we can take maybe one question due to the time limitation.
Okay. Professor, thank you for the presentation. You mentioned that in Thailand, the recycling process is being good, but even though to reach the circular economy is as like in an effective way is difficult. Yeah. So I wonder, would you advocate like for the recycling, or maybe look for alternatives for the massive use of plastics that generate this plastic waste to reach the circular economy? What is your thought?
I thought we're doing both, I guess. In terms of a policy level, we try to ban single plastic use. So the last 2 years before this, we go to the grocery store, we come back with 10 plastic bags. Now we have to bring our own bag. So that part we are doing better and better. Still, the plastic film and the nature of Thailand, I think we have to change that as well. That's why we have some social study at the end, because we normally eat all day, and this is, I'm not sure if it's good or bad, but we normally eat all day. So the plastic mainly is just to carry our food. So once it's contaminated with food, it's not easy to go to the process of separation and recycle. Okay, and so we are promoting that. Try to avoid using a single plastic, of course, until we have this pandemic. So the total scheme changed a lot the last 2 years. And our study, basically everything up until 2018 is valid, but 2019 and 2020 mainly, we cannot make use of that much. We go back to use a lot of plastic at the end. And hopefully after the pandemic, we going back to promote. And we're planning to ban a lot of plastic that it's very difficult to recycle and reuse, and we have that in list. So it's a national policy. Okay.
Thank you.
Okay, thank you. So thank you all the plenary speakers. And now we can move to the student presentation session. So the first speaker is Yura Cho from Korea University, and she will present her presentation on microplastics as emerging contaminants in the environment. So over to you, Yura.
Okay, can I start my presentation? Is it working?
Yes, yes,
Okay.
we can see.
Yes.
And hello, I'm very grateful for the great opportunity to be here, and I'm happy to make a presentation today. I'm Yura Cho from Korea University in KBRC, Korea Biotech Research Center in South Korea. And my presentation is about an introduction or review about microplastics as an emerging contaminant, especially in terrestrial environments. And I may start with the brief introduction about microplastics first. In recent years, there has been a growing concern regarding the impacts of microplastics on aquatic and terrestrial environments, which counts the microplastics as a new type of contaminant. And actually, research of past few years had been mostly focused on the microplastic effects on aquatic ecosystems, especially of the oceans. And you might be very familiar with the pictures of ocean animals suffering with this kind of plastics. However, there was an important finding that 80% of microplastics in the ocean are derived from the land, so that we can imagine how big a source of microplastic the soil might be. And, oh, sorry for that. And even as a sink of the microplastics, people have found that microplastic enters terrestrial environments through varieties of pathways. It could the microplastic could be either as primary microplastics that includes synthetic microplastic, for example, the microbeads used in cosmetics, or as the secondary microplastics, which are generated from the breakdown of larger plastic waste in the environment. Then why the microplastics are considered as the emerging contaminants? Maybe it's because microplastics can interact with several contaminants, such as pesticides or persistent organic pollutants, we call it as POPs, or heavy metals. So it could possibly act as a vector or carrier for transferring these contaminants in terrestrial environments, so that it will be transferred through food webs and accumulated in various organisms as well as humans, which could lead to an unexpected and negative health effects. So even though the microplastics have been recognized as emerging contaminants in soils, still their impact in the soil environment remains largely unclear. But recently we can find more and more reports on microplastic in soil have been released. So when microplastic enters the terrestrial environment, how the presence of this microplastic would affect the soil properties. Before that, we may look at this figure about the sources and fate of microplastics. Microplastics, mostly in the case of the secondary microplastics, can enter the soil by agricultural activity or atmospheric transport or the application of sewage sludge or irrigation. And then it is degraded through the exposure to UV radiation or oxidation or by the biodegradation. Also in the physical way, which could more strongly degrade the plastics through tillage or activity of soil animals. For example, you can see this earthworm. By earthworms, we need digest the microplastics. So the smaller microplastics are generated through these degradation processes and transported deep down in the soil. So once the microplastics deeply got into the soil, it could be consumed by plants and accumulated in plant biomass, which can be finally moved to the body of terrestrial animals and even to humans. Or if it goes far deeper, it may reach to groundwater level and cause the groundwater contamination. So for the alteration of soil properties caused by the extent of high amount of microplastic in soil in physical, chemical, biological way, new findings in different aspects have been reported. First, we can think about the bulk density. The bulk density may reduce with the microplastic since its density is very, very low compared with the soil minerals. And second, once the microplastics are incorporated into soil, it may alter the soil porosity, which can affect the water dynamics in the soil, so that water stable macro aggregates, which are the large aggregates more than 2 millimeter in diameter, and volumes of macropores were increased. Also, the saturated hydraulic conductivity found to be increased by the presence of microplastic in recently reported studies. We can find it. And for the other aspect of soil property, the content of carbon, nitrogen, and phosphorus, or cation exchangeable capacity, which called as CEC, were found to be increased with the microplastic. And so it showed that the microplastics might influence soil nutrient cycles too. And the presence of microplastic could increase the aeration in soil, which is directly related with the microbial activity, which could be the aerobic microorganisms. While they are found to be the increase of dehydrogenase and catalase and proteinase and phosphatase, this kind of enzyme activity, but the activity of urease and cell enzymes and beta glucose were, on the other hand, inhibited with the microplastics in the soil. So there have been important findings of impacts on microplastic on plant growth and the accumulation on plant tissues too. And this is one previous study that investigated the effects of 6 different microplastics, which are the polyester fiber and polyamide beads and 4 other polymers in fragment types. And as a result, we can see that the microplastics altered the plant total biomass and elemental composition of tissues and root traits of spring onion, while the actual effects varied considerably with the plastic polymer particle types. Also, for the smaller size of microplastic, we can see for the right SEM image, mostly the microplastics less than 0.2 micrometer were found to be accumulated in plant tissue by the plant uptake. So these are the micro beads captured by SEM in the SEM image, in which captured the roots and stem and leaves of the wheat. And one of the biggest concerns of microplastics in environment would be its interaction with contaminants, such as trace elements in the environment. The interaction of trace elements and microplastics is found to occur through direct absorption or co-precipitation or the absorption onto hydrous oxides. And it is affected by some key factors. You can see that the surface area and size of microplastics would matter a lot to increase the absorption on its surface. And sorry for this. And aging and weathering of microplastic is one of the important factors too. So it may lead to generate more functional grooves and surface charges on the microplastic surface, so that the surface charge of elements and trace element oxidation status and the contents of oxides are also important factors on absorption of trace elements on the microplastic particles. And if the dissolved organic matter attached particles are present, it's likely to be more interaction and greater retention of plastic particles could happen. And microbial activity also affects the interaction of trace elements and plastics by the production of biofilms. Once the microplastic is degraded and provides a substrate for microbes, biofilm formation is formed, and it can facilitate the chelation of metals and accumulation of trace elements in microplastics. And not only for the inorganic trace elements, but the organic contaminants may also interact with microplastic in soil or more than those trace elements. Due to the large surface areas and hydrophobicity of microplastics, it can concentrate the hydrophobic organic contaminants on their surface. Thus, it may serve as a vector or carrier for these chemicals in the terrestrial environment. And one of previous study revealed that polyethylene film residues could concentrate about 70 times more on pesticides than soil. So, and additionally, chemical degradation, the removal of these organic contaminants in soil could be retarded and slowed down in the presence of microplastic if it is absorbed onto microplastics. And it was reported that the microplastics might accumulated in terrestrial food web at levels similar or even higher than in marine ecosystem, which cause larger impact on the terrestrial onto the terrestrial organisms. And Zhao here found that microplastics are present in the digestive tract of 94% of dead terrestrial birds with diverse foraging behaviors in China. And in some cases, microplastics was considerably smaller than the usual food of those birds, which suggests, microplastic ingestion to be either accidental or through the trophic transfer. And from the other scientists, it has been observed that an increase in microplastic concentration from the soil from 0.87 particles per gram to earthworm cast 14 particles per gram, and finally to chicken feces increased to 129.8 particles per gram. Yes, this kind of increase has been observed, but the trophic transfer of microplastic in terrestrial environments need to be further studied. And finally, I shall move to the conclusion of this presentation. And the microplastics are accumulated in soil, leading to positive or negative impacts on soil properties. And moreover, the combined contamination of microplastics with various persistent organic pollutants or heavy metals and other toxic chemicals can result in harm to soil and terrestrial organisms. And characteristics of microplastics in terrestrial environments, their ecological effects and their underlying mechanisms have not been fully explored so far. So there is a big knowledge gap existing, which we might figure out. And also the mitigating the accumulation of microplastics in terrestrial environment can contribute to the successful achievement of UN SDGs, which is Sustainable Development Goal, such as good health and well-being, or the responsible consumption and production of plastic, and at last, will contribute greatly for the goal of life on land. And this is the end of my presentation, and thank you for listening.
Okay, thank you very much, Yura. So I think we can take students, the question for the students at the end of this session. So now I will invite the next speaker. He's Chao Wang from Nanjing University in China, and he will talk about the enhanced alteration of polyvinyl chloride microplastics by hydrated electrons derived from indole 3 acetic acid assisted by a common cationic surfactants. So over to you, Chao Wang.
Okay, can you see it?
Yes, yes.
Okay. Hello, everyone. I'm Chao Wang from Nanjing University. Here, sincerely appreciate the invitation from Professor Oki and my mentor, Professor Chen Gu. My topic is a little long. Enhanced alteration of polyvinyl chloride microplastic by hydrated electrons. Okay, now allow me to introduce the background of microplastic first. Although it has been well known to everyone here, while plastic brings a lot of convenience to people, it also brings people trouble. Due to large output, strong tolerance, low recovery rate, and other reasons, plastic residues continue to accumulate in the environment, and plastic can be found from the peak to the seabed. Amongst these plastic debris, those of size less than 5 mm, termed as microplastics, have raised great concerns from scientists and the public. Microplastic itself is divided into two categories, primary and secondary microplastics. The primary source refers to plastics that are manufactured in microscopic size, such as abrasive scrubbers used in facial cleansers, while the secondary microplastics are generally derived from fragmentation of large plastics via photolytic, mechanical, thermal, hydrolytic, and biological degradation processes in the environment. With excellent chemical and physical properties, polyvinyl chloride plastics have been widely used in various industrial and domestic products. Since 2006, China has exceeded USA in the capacity of PVC production, becoming the largest PVC producer in the world. However, most of the PVC plastics are laterite without collection, and the presence of PVC microplastic has been ubiquitous detected in various environmental matrices. According to a recent study, the abundance of PVC microplastics could reach 400 pellets per ton in the Pearl River of China. Based on the results of toxicity assessments, PVC microplastic could cause suppressed feeding activity and intestinal damage for different organisms. In addition to its own toxicity, PVC microplastic can absorb other pollutants to increase their ecological risks. The ability to absorb pollutants is also affected by the aging degree. It was well known that several reductive dechlorination reactions widely happen in the environment. As the most active reducing species, the hydrated electron could be generated from indole or its derivatives in aqueous solution and ultraviolet light irradiation. Various organic contaminants have been reported to be reduced by hydrated electrons, such as nitroaromatic and perfluorinated compounds. The hydrochlorination is also one of the most common transformation routes for PVC plastic and natural weathering conditions. Therefore, PVC microplastic distributed in the environments may undergo natural dechlorination reaction with environmental reducing species. However, due to the hydrophobic surface of PVC and the short lifetime of polar hydrated electrons, the reduction reaction between PVC microplastic and hydrated electron would be inhibited under environmentally relevant conditions. Therefore, a proper media is needed to improve the reductive performance of hydrated electron for PVC dechlorination. As commonly used surface active compounds, the cationing surfactants have been extensively utilized in industrial and commercial products. The widespread application of cationing surfactants imply that these compounds are expected to be present in various environmental matrices. It was reported that the concentration of CTB, this surfactant, we call it CTB, could reach about 100 microgram per liter in river water and municipal wastewater. Our recent study reported that CTB could bridge the gap between IA and perfluorooctanoic acid by reversing the intermolecular electrostatic repulsion, thus enhancing the defluorination efficiency by hydrated electrons. Therefore, it is expected that the interaction between indoles and CTB may promote the transformation of PVC microplastic. This is our research method, including photoirradiation system and analytical techniques such as ion chromatography, APR, laser flash photolysis, micro FTR, and Raman. Next, I will introduce our results. This is the dechlorination kinetics of PVC microplastic and different dissolved oxygen conditions. The presence of IA-CTB complex could increase the dechlorination ratio up to 2% and aerobic condition. The dechlorination of PVC microplastic in the presence of IA and CTB will dissolve oxygen dependent, which was in negative relationship with the DO dust. Nitrous oxide has been confirmed to be an effective quencher for hydrated electron, with the production of nitrogen gas, hydroxyl ion, and hydroxyl radical. Thus, reaction solutions were purged with nitrous oxide to eliminate the impacts of hydrated electron. As shown in the figure, a significant decrease in dechlorination was obtained after purging nitrous oxide. The efficient scavenge by nitrous oxide further confirmed the major contribution of hydrated electrons. CTB played an important role in the photo-dechlorination process of PVC microplastic. It was proposed that the formation of IA-CTB complex promoted the absorption of IA on the surface of PVC, thus shortening the transfer distance of hydrated electrons from IA to PVC surface. To further explore the underlying reaction mechanism, laser flash photolysis, APR, micro FTL, and Raman measurements were conducted. The generation of hydrated electron was confirmed by the results of laser flash photolysis and APR. The characteristic signals of hydrated electrons in FFP and APR disappeared when purging nitrous oxide. Compared with the FTR spectra of pristine PVC, a new band at about 11594 was observed. and it is then through carbon double bond stretching. The formation of carbon-carbon double bonds could be attributed to the photoradiated declination process. FTIRS image were constructed for visualization of relative peak intensity based on the absorbance of carbon-carbon double bonds. The intensity order, this is the intensity order, and the strongest intensity was obtained for PVC plus, IA, and CTV. Interesting in Raman spectrum, a new peak around 1510 was observed and strengthened with the increasing time of light irradiation. And the new peak referred to the conjugated carbon-carbon stretching mode. In order to obtain the accurate length of conjugated polysequence, we calculate the polysequence based on the function reported by Barria. And the sequence length was calculated to be in the range of 13 to 15. We determined the absorption capacity of PVC microplastic for phenasthrene and 1-naphtho. A typical nonpolar and another is typical polar aromatic compound. PVC microplastic irradiated in the presence of IA-CTB complex exhibited enhanced absorption capacity for both nonpolar and polar aromatic compounds due to the hydrophobic effects and pi-pi interaction between aromatic rings and polyene structures in PVC microplastic surface. And this work has been published in Water Research, and if you can get access to it if you are interested. This is our conclusion. IA-CTB complex can facilitate photoreductive declination process of PVC microplastic. Hydrated electrons play a dominant role in enhancing PVC microplastic declination. Chloride ion release and carbon-carbon double bond formation occur for PVC microplastic when IA-CTB coexist. The absorption of polar and non-polar chemicals is enhanced for photoalready PVC microplastics. We thank National Science Foundation of China and the International Institute for Environmental Studies, and also thank our group. Thank you, everyone.
Thank you, Chao Wang. So let's move to the next presenter. So who is Viring Kittutamawong from Chu Lang Kwan University in Thailand. So she will talk about the overview of municipal waste characterization and analysis in Thailand. So over to you, Viring.
Okay, let's start. Good afternoon, everyone. My name is Viring Kittutamawong. Actually, I'm a PhD candidate in Chulalongkorn University, and my advisor is Dr. Sutha Khaptian, that who presented already in the third one. And this slide I want to share about our project right now is about overview of municipal waste characterization and analysis in Thailand. So Thailand, located in Southeast Asia, and capital city is Bangkok, or you can call it Krungthep in Thai, which means city of angel, and we have a population around 64 million people. Actually, you can imagine Thailand is a tourist city. We have many culture and many amazing places that you can visit in the future. So, but we have a lot of problems actually. One of them is a municipal waste management. And so I would like to introduce you at first about municipal waste generation in Thailand. Actually, since 2008 until 2019 is quite we generate the municipal waste increasingly about 20%. And if you see in the right side, the picture show the waste generation rate in kilogram per capita per day is around 1.2 kilogram per cap per day. And if you compare with around 10 years, it's increased 13% because of urbanization the city expand into the rural area, and also economic stimulus policy, and also tourism promotion, that because of our country is a tourist destination, and also population growth and as well consumption growth. For the waste composition, mostly Thailand, as Dr. Sutha said, we eat all the time. Mostly the organic waste is around 64%, and the second one is recycled waste, including plastic waste or gas waste. And the next one is general waste, for example, fabric, wood, something like that. And another one is hazardous waste, it's around 3%. So, but the problem in Thailand is the mismanagement. Even from 2008 until 2019, it's decreased around 57%. But if you see in the circle picture, in 2019, we also have a problem about mismanagement around 22%. It's quite a quarter. So it's a lot. And because of illegal combustion or illegal dumping, that we try to get it better and better. Another thing, the good thing is we have increased the good management around and got it around 34%, and other utilization, for example, recycled waste, compost organic waste, or RDF, refuse derived fuel that can burn to the electric, turn to electric. So we care about this problem. So we point to the Sustainable Development Goal, or SDG, by United Nations Development Program. The goal that we focus on is goal number 12. It's about responsible consumption and production, and the target 12.5. We want to reduce waste generation through prevention, reduction, recycling, and reuse. Actually, in Thailand, we also have done it for many years, since many years ago, by waste management hierarchy. As you can see in the triangle picture, we want to prevent first for the most preferable, and then reduce the waste, reuse, recycle, and until the dispose them to the landfill. So for our project right now that we have been doing, the objective is to study the waste generation and waste composition in Thailand. Actually, it is quite a little bit simple, but the thing is, how can we collect the data? It's difficult. This is the difficult part of my work, of our work, that because a lot of data in Thailand, and many ministry take care of it. So we have to collect and want many support of them to get the data. And the thing is, usually in Thailand, we have to study waste generation and waste composition, but it's in year. I mean, they represent in the year, but in our work, we will focus on wet and dry season, also the weekend, weekday, and something like that to see the factor that related to the waste generation and waste composition. And finally, to analyze, the second objective is to analyze the recycling rate. For the outcome, we want to see the waste generation rate, recycling rate, waste consumption, waste flow analysis. Yeah, waste flow analysis or MFA or mass flow analysis is the same as well, but we did it in waste consideration. And finally, we get all the data and we will find some model and find the factor, which factor related to waste generation, recycling rate, and waste composition. For the scope, I think this kind of pathway, I think is quite same for every country, that the source or household generate the waste and transport by the truck to transfer station or to the final disposal. So the red dot is our scope, and you can see the arrow, the black arrow is the point that we want to collect the data. That we expect that recycled waste can emit from this process, and I will collect the data by site survey with questionnaire and search from Google or many things and ask many ministry for secondary data. This is our procedure. At first, we have to region division in Thailand and province selection, next to local area selection, site visiting, and finally data analysis. The yellow one is mean we have doing right now. For the region division, we based on Office of the National Economic and Social Development Council in Thailand, because different region has a different culture and social and also agriculture or career. So we divided into 5, including North, Northeast, Central, East, and the South. And also we cooperate with other university. For example, for the North region, we cooperate with Chiang Mai University and Naresuan University. For the Northeast, we cooperate with Khon Kaen University, and for the Central, we cooperate with Mahidol University. East part is Burapha University, and finally the 5th one, the South region, we cooperate with Songkhla Ratchapat University. Like this team, is 5 team will be cooperate each other and sharing the data, and we can get the data well to analyze in the future. So for province selection, we divided into criteria and main criteria and minor criteria. This part is also quite difficult for our work, because we don't know exactly which criteria that's suitable for the province selection. For the main criteria, we should by province area, population, and household income, and also minor criteria. We have they must have representative of small and large province, and also we consider the waste generation, center of transportation, urban expansion, and also consider the coastal area and island. So finally, we got the 17 provinces. For the local area selection, we have two main criteria: is a community size and economic characteristic. The community size, in Thailand, we separate into the 4 types of community size. The first one is a big city. City municipality is there are more than 50,000 people and so on, until the a sub-district municipality that less than 10,000 people stay in that area. And finally, is a special municipality. It's special because they got it's a province or area that drives the economy in Thailand. So the second criteria is the economic characteristic that we consider about industry, tourism, agriculture, and commercial area. So from the 17 provinces, so we got the 11 city municipality, 15 town municipality, 40 sub-district municipality, and 7 special municipality. And it includes the economic characteristic that we want. All of them. For when we sightseeing, we have to do the quartering method. I mean, for the waste characterization, this is the method that we use. First, we collect the waste and then mix and quarter it and choose the opposite side of the quarter. And finally, we characterize the waste and weight it. For the next one is some place that we visited already, like we sharing what we have done already. We went to Phuket last year. Phuket is a tourist city in southern of Thailand, and this city municipality use the waste incinerator, and with the capacity around 650 tons per day, and they can produce waste to energy around 5 million megawatt. Okay, and also have air pollution control. So this is like one of the results that we want is a waste characterization. When we went there, it's quite a lot of bad smell that I have to wash my hair more than 7 times. And finally we got the data. Gosh. And so you can see in Phuket, the organic waste around 40% and plastic waste around 20%. For actually in that we work, we will divide the plastic waste into many kinds of plastic. For example, polypropylene, polystyrene, PVC, and so on. So it's like for example of result. And another place is we went to Chiang Mai. Chiang Mai also is a tourist city in northern of Thailand and has a population around 1.8 million people. So for the second expected outcome, we want the waste flow. So I did it for the example of the waste flow that we got in Chiang Mai. Actually, in Chiang Mai, they can collect the waste around 290,000 kilogram per day to the transfer station, and they have a consult in their area to separate the recycled waste. And finally, they transfer from the small truck to the bigger truck and transfer to the landfill around 260,000 kilograms per day. It's quite like a example that we want. So finally, from this data that we got from many provinces, we will analyze and summarize that risk factor that affect to waste flow, also affect to the the waste composition. And that's all. Finally, I want to thank the Charlotte University and HHM and also the National Research Council of Thailand that support funding. Thank you.
Thank you, Virin. So are there any questions from the audience?
Sure. So let me briefly summarize for the session for today. So as I mentioned earlier, the public is aware of plastic problem in the ocean, but plastic pollution in the soil is an even greater concern as it affects food security and human health. So basically, if you look for the soil and the soil organic matter, like the soil organic matter, plastic is carbon. So it's easy to collect the plastic floating in the ocean, but plastic in soil or ecosystem is buried. So as a result, no one has looked at how to address this. So people talk about plastic pollution, but it is not yet probably properly regulated by law in each country. So there are many types of plastic pollution that people are not aware of yet. So here, through this meeting, we are aiming to develop this kind of standard and make solid governmental regulation for the future generation. More importantly, I'd like to announce to you that if you look for the newest Polish Forum article published in Science last week, the topic was tracking, targeting, and conserving soil biodiversity. And plastic is now considered as one of the global change drivers, like climate change. So it's really important through this APRU network, it's really important for us to exchange idea and conduct standard experiment in a standard method. I've been recently contacting the very first global soil biodiversity network in the world. The group last week published a big paper in Science, and I was able to contact the director, and we sooner or later we will have the Zoom meeting. But we've been talking about exchanging our samples among the countries, performing the analysis, comparing the data. At the very beginning, the network suggests performing analysis for the plastics or analysis for the soil and water samples, compare the data among the laboratory. The data should be consistent. And then if our group wanted to join as the network, we could be involved in and join this meeting. And at least for Asian or Asia Pacific region, our program can lead this network as a part of the first global soil biodiversity observation network. It's SoilBON, SOILBON. So we have more bigger and impactful research can be done. So I really hope to use this opportunity next time. We'd like to a bit more demonstrate the plastic separation and analysis in the virtual summer school, hopefully. So if you have any additional question or comment, just please feel free to let us know, or you can ask any question directly to our APRU program leaders or our planning speaker or to student, or I think you can communicate through the chatting function even after this event, okay? So I understand the time is already quite late. It's over for 30 minutes. Even compared to the first winter school, we got many more participants today. So just wonder if you have any additional question, we can get just one or two, but otherwise you can visit the website created by Xinc, our contact company. You can leave question there and speaker can leave the answer for the question. So now I'd like to thanks to our APRU Sustainable Waste Management Program leaders. Professor Jang Si-cheng also joined this meeting, Professor Cheong-gu and Professor Chia Wang, Wang Shannon, and Professor Ong from Malaysia. Now he's in UTS in Sydney, Australia. And our program directors, the Professor Bill Mitch, who attended the meeting. So I'd like to ask Tina. I'm just wondering, Tina, are you there? Hi.
Yes, I'm here.
Yeah, so we will try to finish our second virtual winter school, but actually we plan to continue in face-to-face or other through the Zoom meeting within the group. But we hope to see you in next the winter school as well. So could you kindly give some concluding remarks or hello to our student if you have any update for APRU program or anything for us? Thank you very much.
Thank you, Professor Og, and all the speakers and the students. Yeah, it's quite amazing to see everyone has a very in-depth research and studies to share and exchange with the knowledge you have and through this platform. So while I'm listening to all the presentation discussion, I also update our waste management page, so you can have you can keep browsing that, and we can update it. We will update it constantly. So let me just quickly share the web page with you. And 1 second. Okay. So this is the APRU Waste Management website. And I just put the 2 latest upcoming events for the waste management co-organized with Nato and with AICHE. And then if you want to see all the events we have in APRU with other similar or relevant activities, you can find it here at events. And at the events, I also listed all the the summary of the events of this year, and then we'll keep updating that. So I understand we're gonna have the summer school later on, and we'll also keep promoting this winter school and then the following activities. So I think the students are also the key components of this, and hope you can share this information with your colleagues, with your friends and classmates. And we'll also put you on the mailing list, so you can also be up to date with our latest events. And thank you again for all the participations. Thanks.
Thank you very much. Just one more, I'd like to share some information. As I just mentioned, we try to, our APRU Sustainable Waste Management program, our group members are trying to be linked with the main intergovernmental organization like UN, and we try to form a network for global biodiversity or global, the waste management issue, that it's required that at the very beginning, we need to prove our capacity that, for instance, if we look for the plastic in different soil, that we need to prove that by exchanging the same samples, all the analysis should be in a same method, in a same way. And we need to share the old analytical data so that the experimental data comes from different group among APRU Sustainable Waste Management should be consistent and comparable, so that they can be part of the global monitoring data. So yeah, I have a chance to discuss this issue with director of that program shortly. I will update to you through the email. And Tina just showed you about P4G 2021 Summit Seoul. That was our President Moon Jae-in recently announced the P4G Seoul Summit will be held this year. So, so that P4G Summit will be end of May. That will be held in nearby our university, Dongdaemun, DGP. So you can check the website for more information. During the P4G Presidential Summit, our Ministry of Environment, and we plan to co-organize Nature Forum that's related with biodiversity. So I'll update more information to you. And now I'd like to share lastly the upcoming Nature conference. So if you see this one, that Nature conference is already confirmed and website is officially ready. And it is first Nature conference in Korea. It is also the first Nature conference on sustainable waste management. Name of the conference is exactly the same with our APRU program. And APRU, Sustainable Waste Management, is the key organizer. And now we have only 272 days left for the event. You can check all the information on the website, including travel and so on. And yeah, so again, the APRU Sustainable Waste Management, together with Nature Electronics, Nature Nanotechnology, Nature Sustainability, we've been organizing conference, and chief editor of the journal will join the event. Okay, so I really hope to check the website, and abstract submission is already opened. So before we close, I hope our APRU Sustainable Waste Management members actively involved in and make good presentation to the world-renowned scientists and in front of Nature chief editors. And again, thank you very much for joining this long meeting for today, and I hope to see you in the next winter school. And at the end of next winter school, we will talk about standard method, how we can compare the data produced in different laboratory, especially for waste samples like plastics and soil and water samples. And then our next summer, the school will fully focus on laboratory skill and laboratory demonstration. So we need a lot of preparation for that, but I'm sure we can make it. So thank you very much, and you have a great day, and hope to see you very soon. So Kumu, can you give any concluding remarks, and we can finish the meeting for today?
Yeah, thank you very much. And before that, we have two new members who joined recently the APRU SWM program. So I would like to invite Professor Sao Tang and Dr. Avanti Galavitana. Just briefly introduce yourself to our APRU members.
Sure. So we have, as you know, the member university and non-member university. So strategically, the Professor Avanti Galavitana is currently based in Sri Lanka and Yo Paledania, which is the best university in Sri Lanka. But that university is not a member of APRU, but non-member universities still can be engaged in. Yeah, but it's not the program leader officially, but we will work as a team that I had a previously discussion with Christina. So we have APRU members, but non-member partners as well. So just wonder, Professor Igaravitana, are you there?
Yes, Professor.
Yeah. So probably you can give a short address to all of us, and then Professor Tao Zhang from China Agricultural University as well. Yeah.
Yeah, very nice to see you all. I am Avanti Galavitana from University of Peradeniya, and I recently joined the University of Peradeniya. Before that, I was working with Professor Oak at Korea University as a research professor, and also I did my PhD with Professor Oak, and I think now it is almost 10 years I am working with Professor Oak from a long period of time. So recently, our university, mainly our Department of Soil Science, has joined to the APRU Sustainable Waste Management Program as a non-member of APRU to collaborate different things related to the academic activities, including research and student exchange and so on. So our MOU is under process, and so hopefully it will be come to an end very recently. And I think that's all I.
Yeah. Thank you very much, and welcome to join. And Professor Tao Zhang?
Yeah, I'm here.
Yes.
Yeah, I'm here. Okay. I briefly introduce myself. My name is Tao Zhang from China Agriculture University. And recent years, I'm sorry because my computer is the power is lower, so I use my iPhone. I use my now for my introduce. So my iPhone did not have the camera, so I just can use the iPhone. Now briefly introduce myself. I'm sorry. I'm Tao Zhang from China Agriculture University, and recently our group have publication about 60 papers, 24 SCI index papers, and we also handle several projects, and the total funding is more than 6 million. Total funding is more than 6 million, and now I have graduated my PhD program. I have graduated my PhD from Nanjing University in 2011, and then work in China Agriculture University, and I also visit the Arizona State University and University of Hohenheim as the visiting scholar. And now I also as a visiting scholar in Arizona State University in USA and University of Hohenheim in Germany. And now I'm working in China Agriculture University as a associate professor and a PhD supervisor. And our group is focused on nutrient recycling from agricultural waste, especially the phosphorus and nitrogen recycling from agricultural waste. And we have focused on the phosphorus transformation and focus on the innovation technology, and so focus on the P and N transformation from organic P and N to inorganic P and N. And we have do several research. First is pyrolysis assist circulating fluid crystallization technique to recover nutrient. And we have recently publication paper in green chemistry in 2020. It's mechanism and modeling of phosphorus solid liquid transformation during the hydrothermal process of soil manure. And another second highlights for our group research is thermal-assisted engineering biochar adsorption technique for nutrient recovery. And recently, we have publication one paper in Chemical Engineering Journal is ammonia nitrogen recovery from digest by hydrothermal pretreated followed by activity hydrochar adsorption. And third highlight is composting assist valuable nutrient stabilization technology. And thanks to Professor Ock invitation to join in this family, and I will try my best to contribution to I will try my best to contribution to the group. And thank you very much. Thanks to Professor Ock, and thank you to all the members. Thank you.
Thank you. Thank you, Professor Sen. So let me wrap up this session. So thank you very much everyone for joining this event. Especially I would like to thank Professor Yong Sik Kok, the director of APRU SWM program, for organizing this event. And I also extend my special thank to all the plenary speakers as well as the student who presented today in this session. I would also like to thank each of you for participating this event and bringing your expertise to this gathering. So thank you again, and I am hoping to see you during the next winter school session, which will be held in February 23rd. So thank you very much, everyone.